Alright, today we are going to study the expectation values of random variables. Okay, and before introducing this concept, let's review what random variables are. So if we have a probability space, sample space, sigma algebra, and probability measure. Let's say this is sample space and this is a set of numbers, usually real numbers. Then we define a function x, okay, that maps each element of omega to some number. Then if this function x is a measurable function, then this is called a random variable. But what is a measurable function? So let's take a subset of real numbers here. Let's like an interval. Okay, then we take the inverse image of this interval. That is a let's call this set A. Then this inverse image is inverse x of A. Okay. Then this inverse image, if this inverse image is an element of this sigma algebra, then if this holds for any interval of real numbers, then this function x is a measurable function, because each of these inverse images can be measured by this probability measure. Okay. Then, another concept you should know is image. Okay, maybe I should have explained this before. Image of not f of a function x is a subset of real numbers that is mapped from all of omega. So all of omega is mapped to some subset of real numbers. So this is called image of this function. Okay, so that is, let's say, x real numbers such that there exists some omega such that x of omega is this x. Okay, so basically this image of x is the set of all values which this function x can take. Okay, now let's say we have a probability space and we have a random variable to some set. No, this may not be entire real numbers. For the moment, we consider discrete random variable. Discrete random variable. Okay. Then the expectation value of x is defined as summation over all possible values of x times probability of x is equal to x. Okay, remember, this x is an event, okay? So this is just a shorthand notation for this subset, such that this, okay? So again, let's draw this diagram. So let's say we have some value x here. So a certain subset of omega is mapped into this value, okay? So all points within this subset are mapped into this single point x. So this subset is denoted by this notation, okay, which we often write as inverse image of x. Okay, so that's it. Now let's look at this definition from a different angle. To do so, we introduce a little function called Kronecker's delta. Okay, this is defined as this: delta of x and y is equal to 1 if x is equal to y. Otherwise, it's 0. This is called Kronecker's delta. Delta. I think Kronecker is a German mathematician. Please check Wikipedia. Okay, if you introduce this one, we can write this probability as this. So this is the probability that the random variable takes the value of this small x, which can be decomposed into the sum of probabilities. Okay. Now, if we introduce this Kronecker's delta, now this sum is over entire sample space. Then delta x, and random variable of x, and probability of each omega. Okay. This holds because, remember, this is a shorthand notation for this subset. So x equal to x. This is just a shorthand notation for the subset of omega, such that x of omega takes the value of lowercase x. So basically, we take summation of these probabilities over all omegas within this subset. Okay. So now we introduce this Kronecker's delta, which is equal to 1 if this x of omega is equal to this lowercase x, right? So that means when omega is in this subset here, let's see, in this subset, then this is 1. Otherwise, it's 0. So these two summations are calculating basically the same thing. This sums over entire omega, but this delta is 0 outside of this subset. So they are the same thing. So let's use this. Let's apply this uh, modification to this definition. We will have expectation value of x is summation over r x and sum over entire omega and delta x, x of omega, probability of omega. Okay, then move things a little bit. So we write sum over omega first, then sum over x next, then what should we do? X, delta x, and x of omega, probability of omega. Okay, now look at this part. Since this delta is equal to 1 only when this lowercase x is equal to this random variable x of omega, right? And times this lowercase x. So this is actually equal to, we could simply write, equally write in this way. Okay. Because only when this value and this value are equal, this has meaning, right? Otherwise it's 0. So if they are equal, then we can replace this lowercase x with this uppercase x of omega, right? So let's do it. Let's see. So instead of this, we write x of omega here. Then change the order. We could write omega and x r delta omega x of omega pr omega. So we put parentheses here because this delta is the only term that involves lowercase x. So what is this value? This is actually equal to 1. Why? Because within this summation, the value of omega is fixed. So this is a constant. And we vary lowercase x all over the possible values. So only one of these lowercase x is equal to this uppercase x of omega. So in which case, the value will be 1. And in all other cases, the value is 0. So the summation should be 1. Right? So this is equal to omega x of omega and probability of omega. So this can be another definition for the expectation value. Okay, so instead of taking the summation over the values of x, now we take the summation over all the values of omega. So in a sense, here we have sample space and we have some subset of real numbers. In the first definition, we summed over all possible values in here. Okay. In the second definition, we sum over all possible points in omega. But they are of course related by random variables. So whether we sum here or here doesn't really matter. We're actually looking at the same thing. Okay. Let's see. In order to introduce some examples, first let us define the discrete uniform distribution. So let's say we have a finite set of n elements. So this is the sample space. And in that case, we usually take the sigma algebra to be the power set of the sample space. Okay, the power set is the set of all subsets of omega. Okay, then we define uh, the probability measure by this 1 over the size of omega. So in this case, it's since there are n elements, we have 1 over n. Okay, this is called discrete uniform distribution. It's called uniform because this is a constant value. It doesn't depend on which point we are looking at. Okay. But if you remember, the probability measure should be defined for all elements of the sigma algebra. But here, this is defined only for each subset which contain only one of the elements. Right? So it's not really defined for all the subsets of omega. So is that a proper probability measure? Yes, of course. Because any subset of omega can be decomposed into the subsets of single elements, right? So, for example, any subset can be expressed as a union of, not sum, but union of singleton subsets. So singleton means a subset containing only one element. Okay, so if we define this, then we can derive all other probability measures for any other subsets of omega. Okay, let's see some examples. Now we consider a coin flipping problem. So the sample space is made of head and tail. Okay, so that's our sample space, and the sigma algebra is just the power set of this. So all the subsets of this. There should be 4 subsets, and we define probability measure as head equal to 1/2 and tail equal to 1/2. So this is a uniform distribution. Okay. So now we have a probability space. Probability space. Yeah. Then let's define a random variable. Random variable is a function from omega to real numbers. In this case, omega has only 2 values. So x of head is, let's say, 1. And x of tail is equal to 0. So this defines a random variable. So we have head and tail, and on the other hand we have 0 and 1, and head goes to 1, tail goes to 0. That's x. Okay. Now, what's the probability that this x takes the value of 1? Okay, if you look at this figure, so 1, if we pick 1, its inverse image is just one element, head. So this this is a subset, and that subset is a set that contains only head. And this probability x equal to 0. And similarly, we have this is just a tail. And both of them are defined to be 1/2. So, according to the definition, let's say first definition of expectation value, we have, so when x is 1, we calculate probability of x being 1 and 0 times probability of x being 0, and that's 1/2, 1 times 1/2 plus 0 times 1/2, which is 1/2. Fine. If we use the second definition, we will have like x of head and probability of head plus x of tail and probability of tail. So that's 1 by definition, and this is 1/2 by definition, and this is 0 by definition, and this is 1/2 by definition. In either case, we get the same results. All right.